Recall, the definite integral measures the area between the graph and the x-axis. So the definite integral from x equals a to b of f of x is just the area between the graph of y equals f of x and the x-axis from x equals a to b, this shaded region. And the fundamental theorem of calculus tells us that we can calculate this definite integral by finding an antiderivative, big F of x, plugging in the upper bound b and then subtracting the lower bound a. So big F of b minus big F of a. Okay, so this is the definite integral, and it just comes out to be some number. This is some number. This is some number representing the area. In this video, I would like to introduce now the idea of the indefinite integral. And so the indefinite integral is an integral where we just don't put bounds. We don't have any a or any b. And for us, this is just going to be a notation, a convention that's going to just represent the antiderivative. So you should think this makes sense, because if this is to calculate this, we need to find the antiderivative, then this is just going to be a notation to tell us just find the antiderivative. And then later, if you want to, if you're given a and b, you can plug in those bounds to find whatever area this corresponds to. But the difference is definite integral is giving you an area, whereas the indefinite integral is giving you a function. Or more precisely, since whenever you find the antiderivative, there's not just one antiderivative, but there's infinitely many, because you can add any constant you want to at the end, with the derivative still being just little f of x. You could have a +1 or a +2 or +3. So we put plus c here. We have here a function or a family of functions. We have a family of functions which represent the possible antiderivatives of little f of x. So let me give you some examples of calculating the indefinite integral. And really all it is, whenever I say calculate the indefinite integral, remember all we're really doing is we're just calculating the antiderivative. So if I have the indefinite integral of, say, x squared plus 3x plus 1, all I have to do is calculate the antiderivative. And so you go and you say antiderivative of x squared, well, that goes up to x cubed, and then you need a 1/3. Remember how parallel works for antiderivatives. You need a 1/3 because when I take the derivative, a 3 is going to come down. That'll cancel with the 1/3 to leave you just a 1 in front. Plus, the x is going to increase to 2, and then you need a 1/2 out front. You still have this 3, so it becomes 3 over 2. 3 divided by 2. So when the 2 comes down, you multiply by the 2. The 3/2 times 2 gives you just the 3. Plus, the antiderivative of 1 is just x, because the derivative of x is 1. Now I'm saying the antiderivative, it's a little bit sloppy. This is an antiderivative. There are infinitely many because you can have whatever constant you want on the end. You can have a +7 there, you can have a +15, because when you take the derivative, that's going to disappear and go to 0. So I just put plus c. Whenever I'm finding the indefinite integral, I always put plus c. Remember to do that. You had the full family of functions, you always put that plus c at the end. Okay, that example is pretty straightforward. Let's try another one. What would be the indefinite integral, or just finding the antiderivative, family of functions corresponding to the antiderivatives, of x times, say, cosine of x squared. So x times cosine of x squared. Now this one is maybe a little bit less straightforward. It's a little bit trickier. So we're going to need to stop for a second and think about what this could possibly be. So we're thinking about, okay, cosine, how does that work? Well, you might remind yourself that the antiderivative of cosine is sine. The reason for that is when you find the derivative of cosine of x, you get, the antiderivative of cosine is sine, because when you find the derivative of sine, it's cosine. So I did that backwards. The antiderivative of cosine is sine, because when you find the derivative of sine, it's cosine. And so you might be thinking, well, this answer probably has something, maybe something here with like a sine in it. That's a reasonable guess. But now we have some kind of complicating factors, right? We have this x squared piece. And so you might guess, well, maybe the answer is just sine of x squared. Maybe it's just sine of x squared, but let's check. What is the derivative of sine of x squared? When we go and we calculate that derivative, we get cosine of x squared. Okay, this is great. The derivative of sine is cosine. We leave the inside the same. Wait, what's going on here? This is chain rule. We have to use a chain rule here because we have a function, x squared, inside of the sine function. And so we take the derivative of sine to get cosine. We leave the inside, x squared, the same, but then we need to times it by the derivative of that inside. So we need to times it by the derivative of the inside, so we need to times it all by 2x. So it's 2x times cosine of x squared. So the derivative of this would be 2x times cosine of x squared. And we come back here and we look, and that's almost what we have. We have x times cosine of x squared. But the derivative of this would be 2 times x of cosine times x squared. So how do we fix this mess? Like we would love it if there was a 2 here. If there was a 2 here, then that would be the right answer. Well, if once you put the plus c. Always remember that plus c. But we can't just change the problem, right? We can't just put a 2 there. The problem wasn't what is the antiderivative of 2x cosine of x squared. Rather, the problem was what was the antiderivative of x times cosine of x squared. And these are not equal. You know, I'm putting equals, but this is a lie. You can't just put a 2 there. So in order to put a 2 there, to justify that, I also need times by 1/2. Right? So I can multiply by 2 if I also times by 1/2 because now I haven't changed it. Well, you say, well, now this is wrong. Now I have an extra 1/2. Yeah, but the antiderivative of this piece still comes out to be the sine of x squared. Now I just have this extra 1/2 hanging out front. And so now I can just account there's a 1/2 hanging out front. Okay. You might worry, should I have a 1/2 in front of the constant? Well, 1/2 of a constant is just a different constant, so you don't have to worry about timesing the constant by 1/2. Just times the function by 1/2. And now it's correct. You know, if you have any doubts, go ahead and calculate the derivative of this guy. The derivative of 1/2 sine of x squared is equal to, I'm not going to put the plus c because I don't want to take the derivative of c, it's just going to go to 0. Don't even worry about that. But this is going to go to 1/2 of the derivative of sine, we just saw above, is cosine of x squared. Then by the chain rule, times it by the derivative of the inside, so times it by 2x. And as you can see now, the 2 and the 1/2 would cancel. 2 and the 1/2 cancel, leaving me with just the x cosine of x squared. Okay, so this one was a little bit trickier. This one was a little bit trickier. The key is to find the antiderivative. I couldn't just say the antiderivative of cosine of x squared is sine of x squared. I needed a 2x in front. I already had the x, so that was fortunate. But in order to get the 2 there, I needed to get a 1/2 there. The basic thing we're doing here is we're trying to figure out how can we undo the chain rule. When we have the chain rule, how can we undo it? So let's just stop and make a quick observation. The observation is, if I want to find the antiderivative of some function inside of another function, you know, let's say I have some g of x inside of f of x, and I want to find the antiderivative of this. You might hope, you know, your first guess might be, well, the antiderivative of that will just be the antiderivative of f, so we'll call that big F. Remember, the capital letter means antiderivative. So the antiderivative of f we call big F, g of x, and we put out plus c, so good on us, put a plus c there. But that's not quite true, because when you go and you calculate what is the derivative of big F of g of x, you find that the derivative of big F is little f, so it's little f of g of x, but by the chain rule, we leave the inside the same, then we times it by g prime of x. And so what we have here is that this is not an antiderivative f of g of x, this is an antiderivative f of g of x times g prime of x. So whenever you have a function inside of another function and you want to find the antiderivative, you also need the second piece, which is the derivative of the inside function. Like, think back to this example. here I had cosine of x squared. I have cosine of x squared, so I have the x squared inside of the cosine. The x squared is my g of x, which means in order to find the derivative, I need out here the derivative of the inside. I need a 2x outside. Now, to get the 2, I just times by 1/2 and then times by 2, so I have that trick. So I could change that x to make it 2x, but this would have been hopeless. This would have been hopeless if instead the problem had been, what is the antiderivative of cosine of x squared, right? I can't, this wouldn't have worked because you can't just say it's sine. No, this is not sine of x squared. That's not going to work, even if with a plus c. It's still wrong. Right? This is not going to work. You have to have outside of here this derivative of the inside. You have to have a 2x for this equality to be true. Let's look at one more example. Suppose you want to find the indefinite integral, or just antiderivative, of e to the 3x. E to the 3x. So here we go. Now, you have a function inside of a function, right? You have this 3x inside of the e to the. So the 3x is your g of x here. Your 3x is this inside function here. So what does this tell me? This says I can only find the antiderivative if I have the derivative of the inside function on the outside. I need the g prime. So I need out here the derivative of this. So like, what is the derivative of 3x? Well, the derivative of your 3x, the derivative of this 3x piece of the inside function is just 3. So in order to find the antiderivative, I really need a 3 out there. I can't just put a 3 out there unless I also put a 1/3 to cancel with it. Okay, but now this guy's of the right form. So forget about that 1/3 for now. This piece here is of the right form. You have f of g of x, e of the inside function 3 to the x times g prime of x. Okay, I put my g prime in front, it's 3, but there it is. There's my derivative of the inside. Then this is telling me this should just come out to be the antiderivative of the outside function. Well, the outside function is e to the x, so that's just going to remain e to the. Leave the inside function the same. Leave it as 3x. But now, and you can put plus c if you like, but now I have this 1/3 hanging out front I need to stick on. So I tack on the 1/3 from the front. And I claim this is the right antiderivative. So the indefinite integral of e to the 3x, I add that 3 piece there in order to have the derivative of the inside, but then that comes at the cost of also adding a 1/3. And so in my final answer, the answer is not just e to the 3x, but it's 1/3 e to the 3x. And if you're not sure, if you want to convince yourself, do a little sanity check. Go ahead and calculate what is the derivative of 1/3 e to the 3x. Well, the 1/3 stays the same when you take the derivative, but when you find the derivative of e to the 3x, it's leave it e to the 3x times the derivative of the inside. That's times 3, and sure enough, that 3 and 1/3 cancel, leave me with e to the 3x. So you can think what we're trying to do here is chain rule in reverse. So we have to think, well, when I find the derivative, a 3 is going to come down, so I have to combat that by putting a 1/3. It's kind of like when we do the power rule, right? When we do the power rule for the antiderivative, you put the 1/3 out front to cancel having a 3 in the power. Well, here I'm trying to cancel with having the chain rule give me a 3 come out of this, so I put a 1/3 out front. Okay, we're going to develop this more in the next video. We're going to build up something called U substitution, but the big idea we're trying to deal with here is how do you find the antiderivative of a function inside another function, and we're stressing that you have to undo the chain rule. You have to make sure you have the pieces in place to undo the chain rule. So we'll continue this in the next video.